Cool. So I would just start. Feel free to ask questions along the way. I probably have way too many slides than 30, 40 minutes. Though some of them I think you are familiar with, maybe reachability analysis and control barrier functions, so I can kind of maybe spend less time on those parts. But feel free to butt in. At least you described it to me, it's like an open discussion, right?
Yeah.
So yeah, the title of my talk is Revisiting What It Means to Be Safe for Human-Robot Interactions. And this is really motivated by the idea that, when you have robots that interact with humans, safety can no longer mean keep 3 meters away, because for dense, crowded social navigation, for example, this is just not possible. For interactions, we want kind of close proximity kind of operations. And so this really, messes up, or maybe not messes up, but it really makes you think, what does it mean to be safe now, right? Because now it's not a purely distance-based metric. And so I'm going to maybe start with a slide that maybe lots and lots of robotics PhD defenses have for the past couple of years, is, including my own, is the progression of robotics over the years. So before you see these robots, these massive robotic arms on the factory floor that are caged in, preventing from any humans from entering. Now we see that they are operating near humans. I would say they're not necessarily operating in close proximity and interacting with humans, but they're definitely sharing the same space. But the task is still, stay kind of sufficiently far away from the human, but follow them, perhaps, in the case of this probably Skydio drone or something. But now, of course, as we move, to the next generation, the next wave of robots, we want them to operate very close to humans. For example, in autonomous driving, we want autonomous cars interacting with human drivers and pedestrians and cyclists and so forth. So yeah, and so what does it mean? What does the next generation of robots need to have? Or need to do, right? They need to operate in uncertain environments, interact with humans, and perform a variety of tasks. So again, these are probably things that you're all very familiar with. And to kind of scope, put a bit more context to how I'm approaching this problem of designing, the next generation of robots that can, do these 3 things. I'm really approaching it through the prediction, planning, and control stack. So I'm not really going to touch on perception at all. But I'm assuming that within the autonomy stack, there's going to be these 3 main modules: the prediction module, which needs to somehow predict how humans or the environment's going to evolve. And then this prediction module is then fed into the planning module, which takes these predictions and figures out a good path or trajectory for the robot to take. That is, accounting for how the human might behave. And then this plan is then passed into some low-level controller, which will track this trajectory as best as possible. And so kind of with this in mind, there are kind of 2 questions I want to kind of focus on in this talk. The first is, where does safety come in, right? Within these 3 modules, who should be responsible for ensuring safety, right? Should it be the prediction model, whose job to be as accurate as possible? And if that's very accurate, then everything downstream shouldn't need to care too much or need to worry too much? Or should it be the planner that is, accounting, taking these prediction and accounting for how humans behave? And if the planning does, is fully responsible for ensuring safe plans, then the controller just needs to kind of blindly track whatever the planner wants to do. Or should it be the controller that, is really aware of these high fidelity dynamics? It's really able to understand the dynamic capabilities of your robot. Should it be the controller that is in charge of being safe? However, the controller is unable to fully reason about the uncertainty and the complexity of this kind of shared human-robot environment. So the first question is actually, in my mind, not super trivial, right? It's actually not clear where does safety come in. Maybe the kind of the blanket answer is that it should come in everywhere, but maybe the question is how. And then the second question is, what does it mean to be unsafe? As I said at the very beginning, safety can no longer mean keep three meters away from everyone, right? So what does it mean to be safe? Or alternatively, what does it mean to be unsafe? Because ultimately, you're going to have humans in the environment. When you're driving on the road, you actually drive very close to other cars. And so in some sense, you might think that is unsafe, but there is this level of trust or assumption that you have for other drivers to not collide into you. And so the question is, where do you draw that line between, this person's gonna, this other driver's gonna, swerve into you, or they're actually gonna drive responsibly and stay in their lane. And so these are the two questions I want to explore. Are there any questions so far?
No, yeah, I'm good
so far.
Yeah,
okay.
It sounds a lot like the kind of conversations we've had within our lab. The different people in our lab are working on different parts of these three phases.
Okay, awesome. That's good to hear. Okay, so the roadmap here. So again, I'm going to talk about these two questions. So the first half is, where does safety come in? So I'll give a very brief introduction to HJ reachability, and then talk about the approach that I took actually during my PhD on how to integrate safety within the planning and control stack within a learning-based planning framework. So actually, are you familiar with HJ reachability? How much? I just want to know kind of how much detail or depth I need to go into.
I think we're fairly comfortable with the idea of HJ reachability. I don't know if you guys want to disagree, but yeah.
You can probably breeze through the equations.
Yeah.
Okay, sounds good. Okay, they're going to come up in a couple of slides. Okay, so kind of just to reiterate, the kind of the setup that we have right now is, you have humans and robots operating in this environment, and maybe the robot has planned a path based on the prediction that the robot has made for how the humans are going to behave. It has planned a path, but it is very possible that these predictions are wrong, right? You've heard that saying, all models are wrong, only some are useful. And this is the same for these learning-based data-driven prediction models. I'm assuming these prediction models are kind of neural networks, but in general, prediction models are not going to be 100% accurate. So it is very possible that these pair of humans that look like they're dancing could do something completely unexpected, or something that is not captured by the prediction model. And this will cause the robot to, perform some emergency maneuver or drastically change its path to avoid a collision. And this will cause the robot to no longer be able to efficiently reach its goal, which is the target shown on the top right. And so the goal here is to develop robust control techniques that ensures the robot is going to be safe, that ensures the safety of the robot without unduly impacting planning performance. So we don't want to sacrifice our planning performance, right? It's kind of like, can we get the best of both worlds? Can we be both safe and still achieve, high level objectives like reach the goal, maintain speed to some extent, not drive, not slam on, have kind of minimal control effort, for example. But we want to do it to the point where we're not sacrificing too much of one or the other. And so here are the introduction to reachability slides, which I'll just breeze through. And so the idea of HJ reachability is to kind of ask the question, does there exist an ego policy to avoid a collision, assuming a worst case contender policy? So I'll use the word contender to indicate the human agent, or someone that's not the robot, and the ego as the robot here. And so really you can think of this as computing a backward reachable set from a set of collision states, where being inside the backward reachable set means you're going to enter the collision set, or you will definitely enter the collision set if the contender is doing the worst thing possible. Okay, and so in order to solve this backward reachable set, or tube, which is there's a slight terminology difference, but not super important here, is the way we can solve this is to solve the HJI partial differential equation, which hopefully you have seen before.
Yep.
Okay. And kind of the outputs of solving this PDE is this HJ value function, where the value function is negative if we're inside the set and positive if we're outside. So being inside the set is bad because it means that we're gonna collide if the contender does the worst thing possible. So positive values are good, negative values are bad. And also with this value function, we can also get the optimal collision avoidance policy for the ego, which is simply the control that maximizes the kind of the dot product between the gradient and the dynamics. What we can also do on top of that is not only compute the optimal collision avoidance policy, but also compute the set of states, set of controls U that keeps that gradient from being non-negative. So the optimal one is usually a bang controller, so it's going to be using very kind of exaggerated, very kind of extreme actions, controls for the ego to avoid a collision. But we also want to say, well, there must be other controls that can keep the robot safe, but maybe not as extreme. And so we'll call this set U safe. Is that okay so far?
Okay.
Cool. So kind of takeaway here is that we have HJ reachability. We can compute this HJ value function. With this HJ value function, we can compute what is safe, what states are safe and unsafe, and also the set of controls that keep the system safe. And kind of the idea of and so kind of the approach that I'm taking is actually, maybe not too surprising and pretty straightforward. And the idea is that your planner, I guess I didn't have a slide to show this. Okay, but basically your planner could be anything you want. In this case, in the experiments I'm going to show you, the planner is actually using a neural network prediction model of what the human's going to do. And then the planner is going to make a plan based on that. And then that's going to spit it to the controller, and the controller is just going to track that plan. But the problem is, what if the prediction model is wrong, or your planner makes a mistake? Then your controller is just going to naively follow this bad plan. And the idea is to have the safety monitor on the side that is keeping, kind of basically monitoring, is your system in a safe or unsafe state? And if it realizes that it's in an unsafe state, then we're going to add an additional control constraint to our trajectory tracking controller that says we're going to activate this HJ safety preserving control set constraint. So basically it's that, yeah, go on.
Sure, yeah. But then you have to make assumptions on like what the maximum disturbance of the human model could be, right?
Yes. Yeah,
Okay.
You have to make that. I'll go, which is,
Probably coming up.
yes, you have to make some assumption, but I'll talk more about that in the second half.
Okay.
But basically the blocks in orange here is this optimization problem for the controller, right? The controller is just saying, I want to minimize tracking error, right? I want to do whatever the planner tells me what to do, subject obviously to some dynamic state and control constraints. However, if your system is in an unsafe state dictated by this HJ value function, then what we're going to additionally do is add a control constraint that says the control has to live inside this safety preserving control set. And so ultimately what is happening is that your controller is still doing what your planner wants to do, right? However, but subject to this HJ constraint. And so this allows the robot to kind of balance between tracking performance or planning performance and safety. And this is in contrast to just switching to the optimal collision avoidance policy, right? Kind of traditionally, and what has been done in the past is if your system enters an unsafe state, it would just switch to the optimal policy. And this is, in some cases, that is really good, right? Like, I mean, in some cases that's okay. But if you're talking about having passengers in the car and then suddenly you slam on the brakes or do this hard swerve, it's not comfortable. I've been in the car that did that. It is not pleasant. And so you really want to have some approach that is, you know, what I have in the title here, minimally interventional. You want this to be kind of as seamless as possible. Okay.
Also, a related question. So are you solving the HAV over like an infinite horizon or some finite horizon? Because that would affect when the intervention starts, right?
Yeah, so that's a good question. So in this work, depending on how you set up the dynamics, like that will converge after a while. And so we just kind of solved it for a long time until we said, okay, this kind of converged and kind of did it as that. So in theory, this is what we did, at least in these experiments I'm going to show, is an infinite horizon. But maybe you could choose something else.
Up to steady state. Okay, cool.
Yeah. Okay, and so I have a couple of videos that I took from a simulated experiment. And in this first run, we're doing tracking only. So this is the case where, if I go back, this is just running kind of the nominal prediction, planning, and control stack without any safety monitor. And so the controller is just going to do whatever the planner wants to do. But in this experiment, the human car, shown in green on the right, that's me on an Xbox controller. I'm going to just swerve, kind of unexpectedly swerve into the other lane. So I'm going to just unexpectedly swerve into the robot. And the robot is on the left in the red. You see the little bubble there, that's the backward reachable set or the backward reachable tube. You're going to see a bunch of lines coming from the human. Those are the robot's prediction of what the human's going to do. So I mentioned before, I was using some neural network prediction model. And then you're going to see a line coming out of the robot, which is the robot's planned path, okay, or planned trajectory. So I'm just going to play this video and then it'll make more sense. And then you see that I swerve into the robot. I don't know how it is showing up on Zoom. Maybe it's a little choppy.
It's not bad, yeah.
Here I suddenly swerve into the robot. And the robot actually tries to stop. You can see that the planned trajectory is red. So it's trying to slow down to avoid it. But the planning frequency is just not fast enough to really respond to these sudden changes to the environment. And unsurprisingly, a collision happens. And this is to be expected, right? This is kind of the baseline nominal case. In this experiment, the same setup, except here we're going to switch to the optimal HJ collision avoidance policy. So this is the one where we just suddenly switch, and I claim that this is going to be too extreme and planning performance is going to suffer the most. And so you can see as I swerve, the red car is able to react really quickly because actually something I didn't mention, the controller is running at a much higher frequency, right? The controller is running at 100 Hertz. It's able to really respond to these very, very fast changes in the environment. And so you can see the green suddenly swerves, the red car is able to swerve away, but to the extent it's completely gone off the road. It's off. Imagine this was the highway, for example, there could be concrete barriers, there could be another lane, this could be, I was going to say the other side of traffic, but maybe in Australia or in England, but you get my drift. And then finally, this is the approach that I'm proposing, which is to treat this HJ control safety preserving control set as a constraint only when necessary. And this is able to ensure that the robot can balance performance and safety in a principled way. And so you can see that the green car does swerve. The red car also swerves, but not as extreme, right? It doesn't, it swerves only to the extent necessary to stay safe, but very quickly it gets back on track to finish the lane change maneuver. Okay.
Cool.
And just to kind of show, it's not going off the road that much. It does a little bit because it needs to avoid a collision, but it's not to the point where it's not coming to a full stop or completely off the road.
And
so
that
the
happened even though you're comparing against a worst case policy?
Yeah, so all this is done using this, assuming a worst case policy when computing the reachable set. And so you can actually see it's not great because these sets are very wide, right? They're so wide to the point where if the green car was to edge a little closer to the center lane, like the center line, the red car's going to think it's unsafe, which is not very practical. And I'll actually, this is a good point, and this is a good segue to the second half of my talk. Right? Can we loosen this? Can we relax this worst case assumption? And just to show you a video of this working on kind of a full scale vehicle. So this vehicle here is X1. It's called X1. It's kind of designed by another lab on campus at Stanford. And X1 here played the role of an autonomous car. And then no one would give us a second full-scale car to deliberately drive into X1, which maybe understandably so. And so the next best thing was to get a little 1/10 scale RC car with lighter visible flag to track it. So let me, I don't know if you can see it, there's a little RC car right here. But on the bottom left, you can see an overlay of their positions, similar to the simulated setup that you just saw. And then you can see the RC car is going to swerve into X1, and X1 is able to kind of nice and smoothly, swerve away to avoid a collision and actually cut in front of the RC car. So yeah. Okay.
So X1 is thinking that the RC car is as big as a normal sized car.
Exactly. Yeah.
Okay.
So the RC car was really tracking like the center or the center of mass of the of the car based on our dynamics model. And so I ran a bunch of experiments on the car and did it for the three different setups, right? The tracking only, the switching, and kind of the one where we're treating safety as a constraint. And so in terms of a safety versus efficiency plot, ideally we want to be on the top right, where we're both safe and both efficient. And so in the red, this is the first case that we saw. This is the one without any safety monitor, no reachability, anything, right? This is just kind of the controller naively doing what the planner wants to do. And you can see that we're the most efficient, but in terms of safety, there's a huge spread. And there's a spread because there's this is a probabilistic planner. So this is not great. There's really no kind of confidence or assurance on how safe your system's going to be if we kind of just did the tracking only case, the one where we're just following what the planner wants to do. In the yellow is the switching case. This is the case where we switch to the optimal HJ controller, and you can see we're the safest. But in terms of efficiency, we do very poorly. And this is maybe not too surprising because this corresponds to a lot of hard braking and hard swerving maneuvers. And then what we have.
Are there some cases without total, like why are there some cases with negative safety in the switching controller?
Oh, this is okay. So negative safety here. So yeah, I'm integrating the value function over the trial run. And so, yes, this is due to model mismatch.
Okay.
There's model
So this
mismatch.
is the experiments, the one that you
Yeah,
ran
real world
in-
experiments.
Okay,
In
cool.
the simulated, it should be fine. But in the real world, yeah, there's just immense model mismatch between what we think X1 can do versus what we thought it could do in the reachability computation.
Okay.
And then in the green is kind of, you know, the method we're proposing, and you can see it kind of fits right in the middle. It's maybe not as efficient as the red, but it's close, and it's almost as safe as the yellow dots. And so, you know, I would say this is a good plot to kind of show that we're really kind of in the middle, where we have the best of both worlds, both safe and efficient. Cool. So that kind of sums up the first half of the talk. If you want to learn more, I have a journal paper on this work with more experiments kind of detailing the different elements of the approach. Right, and so this is a question that one of you had brought up was, isn't the worst case assumption on the contender too strong? Right, like is it impractical to operate under the assumption that the contender, so humans, are always going to behave adversarially? And the answer is yes, right? It is too strong. On the one hand, you've got to, you know, you could argue that you need to make this assumption in order to make any guarantees or strong assurances that, you know, we're going to be safe, but it's just not practical in these dense interaction settings. And so this leads to the second half of the talk. What does it mean to be safe? So we're going to revisit the reachability formulation and then talk about how we can actually learn some of these parameters from data. So to begin, I want to just maybe show you this scenario and ask, you know, is the autonomous car safe, right? So given that you have these two cars in different lanes and they're going to merge into the same lane, is the autonomous car safe? Should it execute a safety or emergency maneuver to avoid a collision? And I guess, do you guys have any thoughts on this question?
Well, if I was driving in that situation, I would start to, well, my car's not very powerful, so brake, or at least brake or accelerate, like something different.
Right, you would do something different, right? But I would say it depends, but this would depend on what the human's doing, right?
Yeah.
But like if you had to say, just given this snapshot, right? If you knew what the human's position and velocity is at that moment and your own velocity, like you just I had to ask you, are you in a safe or unsafe state?
Well, no, it looks like there's going to be a crash. So
because of the way I drew it.
Yeah, sure.
I don't know, if they're far enough apart, then it'd still be safe. If they're like within a meter of each other and they still haven't resolved this merging spacing, then yeah, by then they're probably unsafe even if they haven't crashed, but they're potentially safe if they're further apart.
I guess like a normal assumption is you continue on the trajectory at the same velocity that you are. So if you're assuming like the same states
So if the autonomous,
continuing, then you'd be unsafe, right?
yeah, if the autonomous car just follows, like if it doesn't have another planning step, yes, it's unsafe.
Yeah.
Yeah, so I think the common theme in these kind of responses is that it depends on what you think the human's policy is, or what the autonomous car's policy. Like if you assume everyone's just going to maintain speed, then maybe yes, that they're going to collide. If you assume that in these kind of situations, the human is going to just slam on the brake, like maybe the human also thinks it's close to being unsafe and the human's default response is to slam on the brakes, then maybe the autonomous car is safe, right? If the human slows down, then the autonomous car can proceed as normal. And so really this is a trick question, right? Because there's a lot of factors that come into play into determining whether or not the autonomous car is safe or unsafe, right? It depends on the human behavior. There's a bit of uncertainty in that. It may depend on road geometry, depending on how what the road looks like. That could affect, is it safe or unsafe? And I mentioned this before. There's this interesting notion of responsibility, right? Maybe in this case, the human driver has a right of way because the autonomous car is the one that's merging. So maybe the human driver has a right of way and the autonomous car should stop, but if it's not, then it is unsafe or something, right? But there's all these kind of factors that we need to consider, which makes answering the question, is the autonomous car safe, tricky. And to kind of make matters even more complicated, there's a lot of different stakeholders kind of in the autonomous and the AV field, and they all have different assumptions. They all have different assumptions, and there's really no consensus on what they all think safety means or doesn't mean. And so that makes it even harder. But I think the good news is that, I think IEEE has a working group on kind of coming up with a document that really outlines what are the bare assumptions, what are the minimum assumptions one must consider when defining safety for an AV.
Do they define it in terms of like safety over a horizon, or is it like do they? Yeah. Okay, I guess I just have to go and look at what they.
Yeah, I can find the document and share it. It's like, it's not very. It's like they're not proposing a particular branch of control theory or anything. It's very qualitative.
Okay.
It's like a car shall not do this in this situation, and you're like,
okay.
okay. As long as we yeah, it's kind of vague but specific at the same time.
Okay. Do they consider like different like you have the division of responsibility? Is that part of that idea? Like who has the onus of safety?
No, I don't believe they really talk about it too specifically, but there's another paper I can share, which talks about this concept of duty of care. So if everyone follows their duty of care, then in theory,
sure,
you should be fine. And if a collision happens, but you are keeping to your own duty of care, then you are not at fault. There's also kind of this kind of these legal terms and legal considerations trickle in as well, which I tried reading some of these like legal language, and it's very confusing. I need a law degree or something to read it. But anyway, I hopefully you understand kind of the complexity of the problem where we're faced here. And to maybe take a stab at this, first I wanted to kind of have some framework or terminology to describe safety. And so I kind of just made up this term safety concept. It's not too, like, again, this is something I made up. It's not like in a textbook or anything, but I think it's just like a nice terminology and framework for the rest of the discussion. So I've defined safety concept as two functions mapping from world state to two things. One, a safety measure, and two, a set of allowable safe controls. So the safety concept can be as complicated or simple as you want, but basically, given some snapshot of the world, it can tell you how safe is an agent and what are kind of allowable and unallowable things that the agent can do to stay safe. Okay.
And here by controls, you don't necessarily mean like an instantaneous control. You mean like it could be a trajectory, or it could be some sort of plan. You're keeping it general in that sense, right? It
could be general. It could be like, these are the open loop plans that you can do, or right. It could be. It's very vague, right? Like it can be as complicated or simple as you want. But it's just to kind of say, different people have come up with different safety concepts, but at the end of the day, they're just saying, is this agent safe or unsafe? So there's some kind of measure. But when I say measure, I literally mean like a number.
Okay.
1 or 0? Is it negative or positive or something? Not like a mathematical measure or anything. Yeah, and then just some set of these are the safe things it can do, and these are the unsafe things it shouldn't do. And you know, maybe I chose this in a convenient way, but it turns out that sorry, HJ reachability can be viewed as a safety concept, because the HJ value function V tells us how safe or unsafe your system is, right? Remember, positive values were good because it means you were outside the backward reachable set, and negative values were bad. It means you were inside the backward reachable set, which could lead to a collision, assuming worst case assumptions by the contender vehicle. And then the safety preserving control set is telling us a set of controls that keep your system safe. Great, so kind of what this is telling us that by solving this HJ reachability problem, we have synthesized a safety concept. Right, HJ value function is the safety measure, and the safety preserving control set is the allowable safe controls. But going back to the kind of point that was raised before, was that this worst case assumption of the ego, the worst case assumption of the contender is very strong, right? The strong assumption. But there is no reason why we can't change the control bounds of the contender vehicle, right? Instead of assuming the contender can do literally every possible control, and this is what this capital D is saying, we could just change it up. We could maybe say the contender can only brake, just for fun. We could say maybe the ego can only accelerate. You know, we could. I mean, this is just a HJ reachability problem. We can choose what these control sets for each agent could be. But by changing it up, you can think of this as like a tuning knob to the types of backward reachable sets we could come up with. And this is just an example to show that if we assume both agents have the same control authority, you get the solid line. If we assume that agent A can't go as fast because maybe it's trying to merge onto the highway, so the speed is slower than agent B, for example, then you get a totally different set. But this is just to illustrate that we can view the control sets, capital U and capital D, as like tuning knobs to come up with different value functions and therefore different safety concepts. And then, and just to and so this is basically saying that we can view HJ reachability as a way to describe a family of safety concepts. Again, safety concept is a very vague and general term, and here we're just describing a specific family of safety concepts. And this really depends on how you choose these control sets, capital U and capital D. And so we can describe a whole range. We can even describe open loop policies. Maybe it's using HJ reachability to solve it, maybe is a bit of an overkill, but we could do it. And we can also describe closed loop reactive policies, and we can describe a whole range. And then you probably have seen some of these terms in some controls papers, like forward reachability, reach avoid games, worst case dynamic games. So that's HJ reachability. In industry, safety force field is used in NVIDIA, and responsibility sensitive safety is used by Mobileye. You might have heard of velocity obstacles and contingency planning. And the claim here is that you can view all these as a type of reachability problem, and also a type of an example of a safety concept. Yeah. So depending on how you frame some of these, depending on your contingency planner, or but like you can, basically all of these terms that I have on the screen can be written as a reachability problem, which is maybe not too surprising, but it was surprising because a lot of these concepts were developed without reachability in mind. And so I thought that was kind of cool. Anyway, so I have a preprint, just like a short paper kind of describing this idea of safety concepts, how reachability can describe a family of safety concepts, and how we can actually recover a lot of existing safe control methods using reachability. Okay, but now I have a couple more minutes, and this is maybe the latest results part. And so what I have here is, again, the HCA reachability, the HAI equation. And so here we get to choose what I just said was that we get to choose what capital U and capital D is. And what would be really great is that if these control sets U and D depended on state. So if these control sets were state dependent, because we're saying in different contexts and different scenarios, people might behave differently. It might, in this scenario, this person might be expected to yield, and therefore their control set's going to look very different. And so the goal is to learn U and D that are state dependent. And how do we do that? We can learn this from data. However, once we, yeah.
A small question here. Do you think it can also be made dependent on the history? Like, for example, if in practice we have been seeing someone slowing down, then we can make more assumptions about how that person is going to behave compared to just observing that, okay, it was moving at 50 miles per hour, but if the person was moving at 80 miles per hour and had slowed down to 50, then it means it's probably going to continue slowing down.
Yeah, that's a good point. It will be, yes, I mean, it'll be, that will give us a more informative or more accurate control set U and D. I don't know if that also means that your HA reachability state, or like the state X, also is going to be a history, which, as you know, like this is not very scalable. They could be, you know, obviously we could use the HJIPD as like a inductive bias to maybe learn these value functions. But if we're just going to solve it explicitly, which is what I've been doing, it won't scale.
But you also lose the Markovian property then, right? Because then you can't use dynamic programming anymore if you have a history involved. At least not directly. Maybe there's ways in like belief state planning, but you know, like the whole way of solving this AGB or the way you derive is from dynamic programming. But if you include,
I mean, what if there is like a single extra state which somehow encodes the history? For example, I don't know, I know that the hidden state in LSTM networks, that's basically used to store history. It's like a single neuron, or it can be multiple neurons, but in theory it can be a single neuron that somehow stores what's the effect of the past on the present.
Yeah, but then that ultimately means you're back to a state, like an extended state.
Yeah, but that state must have some special properties. I guess. Sorry, that was just like more of a research-oriented question. Like possibilities of what we can do with this problem.
Yeah, no, that's fine. Yeah, that's a good question though. Yeah, I mean, as I say, like if we do just kind of extend the state, augment the state, I think the reachability computation would just fail. But maybe there's something a bit more clever you could do, or something.
Can I ask what toolbox are you using for reachability computation?
Yeah, it's the one developed at Stanford. It's basically the same as the Berkeley's toolbox, but written in JAX, Python JAX. Nice. So it's much faster. And
you need that.
Yeah, I need that. I've been doing a little bit of reachability lately, and so.
But in MATLAB, I think you were trying to use the original from Berkeley. Right?
Yeah, I was using the helper OC and level set toolbox, but.
No, you use. I'll send you some follow-up links and stuff on.
Nice, that'd be
great. All this stuff.
And you'll send them out to the rest of us, right?
Yeah, I'll put it on the Control Conversations webpage.
Okay.
Yeah. Thank you so much.
Thanks.
Yeah, of course. Okay, so we're saying we want to find U and D that's state dependent. But if we kind of naively plug it just into the reachability formulation, it actually becomes there's like a coupling that's happening between the two agents. And so what we actually end up is a constrained game theory. It's a constrained game. So okay, I'm rapidly running out of time, so I might kind of go a little fast. So the first So the first thing is, can we learn a state-dependent control set? And the answer is yes. If we have the data for it, we could learn it, right? So basically, imagine we had all these, for the same state X, humans might, for a given state X, humans might execute different controls, right? Because humans are inherently stochastic, right? They're not going to repeat the exact same control every time. And so the idea is that, maybe these crosses are all the different controls humans have taken for the same state X. Basically, we want to learn some boundary that encloses all those controls. And we want this set to be kind of as tight as possible. And the assumption is that the reason why we don't observe a human taking something outside of this set is because it's unsafe. This is an assumption, right? The reason they always, in this particular state, they always slow down and swerve is because they want to stay safe. You won't observe anything where they will be speed up and go straight, because doing that will lead to a collision in the future. So that's kind of an assumption I'm making here. And based on this assumption, this is just also then saying that humans, when you observe human state and controls, these live inside a control invariant set, right? Humans operate inside a control invariant set. They don't want to exit it because it means they will end up in an unsafe situation, right? And so I'm sure you all know what a control invariant set is, so I won't go into that. And so the question is, can we learn a control invariant set from some driving examples? And the answer is yes. And the way we can do it is to actually learn a control barrier function, right? Because control barrier functions describe a control invariant set. Control barrier functions are nice because, they kind of have some interpretability into what be and how, and they depend on dynamics. So that's kind of like a nice inductive bias to learn these control invariant sets. And so the question is, can we learn a CBF from data? And there's some existing work on doing it, so this is maybe not too surprising. But what I actually do instead is, there's a bit more details in the paper, but basically I assume I know B, and I'm actually learning parameters of alpha, just to make this learning problem very, very simple. And the reason for that is that when we're driving, I feel like if the obstacle is known, everyone's trying to avoid the obstacle. So there's no ambiguity on what B is, right? Like everyone is trying to avoid the same obstacle. So in my mind, B should be known. What is unknown is how people avoid the obstacle. And that is described with the alpha function. And right.
Yeah, I'm actually happy to see you talk about it, because my research has been about finding and tuning alpha so far, and most of the people tend to ignore it. Like most of the learning CBF papers, they still try to learn a barrier function which for a given alpha and given control input bounds can be satisfied with this equation, but not many people focus on tuning and finding the alpha itself, assuming a given barrier function and given control input bounds. So that's what actually I have worked on about.
Okay, yeah, we should chat as well.
But mine has been more about online adaptation. So yeah, but I'd love to chat about this more sometime.
Yeah, okay, cool. Okay, I'm gonna blitz through this. But I mean, maybe you get the idea. You have some data, we learn the alpha from the CBF. And so that's the idea. So now after we learn the CBF, we now have state dependent control sets. And then this is now this is in contrast to assuming worst case controls from the contender. And so the next question is, how do we take this CBF control constraint into the reachability formulation? Right, basically we have this reachability formulation, and ideally we want to get this CBF control constraint happening. I'm not going to go into the details, but this is basically a couple, like a constraint game. There's a bit in my paper, I have proposition that you can actually swap the ordering a bit to make it work. Because you don't want the first player to select a control that makes it impossible for the second player to satisfy the constraint. Right? So both people are actually constrained, right? Because if the first player could do absolutely anything, then it is possible for it to screw the second player. So you just have to make sure that the first player picks something that is feasible for the second player as well.
So when you're solving this HJB, do you need to solve a linear program within your lowest level of HJB?
In theory, yes, but in this setup, the controls were only 2-dimensional, so I kind of brute forced it, which is not the most efficient way, but I brute forced it.
Okay, cool.
And then
brute force meaning you enumerated the corners of the set. Okay, cool.
Not very efficient, but this was all done offline.
Yeah, and for 2-dimensional, it's possibly as fast or faster as a linear program.
Yeah. And then and here you can just kind of show, you can see the different sets. The black one is the worst case assumption, and you can see that it's very wide, which is similar to what we saw in the first half of the talk. And then the green one is kind of the proposed kind of CBF version, where you have these state-dependent control sets, and it's much slimmer, which which I guess is consistent with our thinking that if you have a car kind of nearby, we're assuming it's not going to just adversarially swerve into you. And so, yeah, even though it's just this plot here, like I was really excited to see this plot because you can just see how less wide it has become based using these state-dependent control sets. I'm really sorry I'm going over time, but you can kind of read more about it in this paper. It got accepted to ACC, so I'll be going to ACC this year, but it's up on archive. And then, yeah, and that's kind of the end of my talk. So what did I talk about? I talked about ensuring safety is important for when designing robot algorithms for human-robot interactions. A lot of my work uses HA reachability. I like it because it's interpretable. It gives you some kind of guarantees in some sense, but obviously it's limited in many ways. One is scalability. 2 is the assumptions that you need to impose on other agents. Usually it's the worst case, which we saw was like not ideal. And then so I kind of showed that we can maybe learn from data, these state-dependent control sets, and kind of reduce the over-conservatism that is usually kind of embedded in the HA reachability computation. So
that's really cool. Yeah.
But yeah, thanks. I know some people had to run of a class or something, or midterms. But I really enjoyed your questions, and I think we should definitely chat more with a lot of you. I should definitely chat with a lot of you offline.
Sounds good. Yeah, I was just wondering, have you looked at these stuff on using neural nets to solve HJB equations?
I haven't. I know there's some work by others that do it. And I need to kind of look into that.
There's some pretty impressive stuff there. There's like a small example in Julia that shows solving a 100-dimensional HJB equation in like minutes.
Oh, really?
Yeah, so I know HJB normally is like computationally, like it scales really poorly, but there's a bunch of papers out there now that suggest that HJB can be solved without the curse of dimensionality using neural nets.
I'm not sure. So the levels are toolbox you're using from the Cornell group, Berkeley group.
Yeah,
Berkeley, right? Yeah, the
Berkeley.
Okay. That one sort of maintains a table, right?
Yeah.
So that's the idea behind using function approximations.
Right.
So instead of maintaining a table, it's like a single function, in this case, a neural network, which just tries to approximate the table.
Yeah.
So it becomes much more efficient.
Exactly. Yeah.
I think in practice, if it converges really nice, then it can be said to have theoretical guarantees of having the correct answer, which in most cases it will converge if the neural network is large enough.
If it's large enough, and it doesn't have to be that much larger. I think they used like 2 layers that were like 10 or so neurons larger than the dimension space.
Yeah.
So it's like not that difficult. And I was like pretty impressed. I haven't really used it myself because I'm not that familiar with neural nets, but I'm definitely going to
Yeah.
start looking into it as potential toolboxes or methods.
I think
Do
what
you
will be
know
interesting
who is
here
it by?
Sorry?
This was literally just an example by the guy who wrote the library. But there's a bunch of papers I can link you to that show various techniques and show some convergence properties, or like they show that if you have the viscosity as part of your formulation, then the AJB converges better. Yeah.
And you said it was in Julia.
And this one is in Julia, but I know Sylvia Herbert's group has a toolbox that also does, I think they call it deep HJB, where they try and solve.
Oh, I know Sawmill has Deep Reach.
Oh, that's one, yeah. Deep Reach
Yeah.
is one of them.
Gotcha. Yeah, I haven't really looked into neural nets. I know there's some work that learns a value function offline and tries to improve it online.
Okay.
So that could be useful. But stuff I'm kind
Yes.
of thinking about but haven't.
Okay, yeah. So yeah,
I need
this deep
PhD
reach is, I
students.
think-
I need money, and therefore I
Ah,
can get PhD students.
yeah. You've just started as a new professor, right?
Yeah.
Yeah. I was just talking to my professor yesterday, or not recently, about how it was getting started. And she was like, "Yeah, it's really tough."
Yeah.
Yeah.
Like I think even now we do face the pressure sometimes that our funding is gonna end. So either we somehow arrange a new funding or we graduate. And I don't know which one is easier.
Yeah. Here is the link on the 100-dimensional example. The dimension is literally just a parameter that you pass in, and it, like, you can see the code is really, really short.
Oh, it's called neural P. Oh,
Neural PDs is like a whole category of methods of solving standard PDs, but using neural nets. So they essentially encode the solution as a neural net.
yeah, I wonder, I guess solving it with so this is just HJB, right? Like HJI is a little more
Sure,
complicated.
I'm sure you
but
could extend this to AGI as well.
yeah, something like that.
Yeah.
Cool. Okay, so I have to run, but I will thank you for inviting me. This was really, really fun.
Thanks for coming.
amazing.
Yeah, it was nice to have you.
And yeah, I'll send a follow-up email, and I would love to connect with, I think, everyone. I think everyone, there was some connection there. So I would love to chat
Yeah.
more and kind of see what you're up to and see if there's any kind of
Yeah, absolutely.
overlap
There's
or
place
potential for
collaborations.
collaborations.
Yeah.
Yeah.
Absolutely.
Okay,
It's really interesting. All right, thank you so much.
cool.
Thank you.
Thanks everyone. Enjoy your midterms.
Bye.